Okay, let's see what to be reminded. For your programming test number 1, the result, we are basically done with the grading, but there will be some result to process, some stuff and generate a feedback file for you. It will take some time, but by the end of this coming Friday, you should really receive the result. May not be in time before your written test number 1 on Thursday, but I don't think they're really related. So I would say for written test number 1, you just make sure you kind of read through the solutions for Lab 1 and Lab 2, and also the highlights that we discussed in the class. That should be the very promising first step to really go over the material. Okay, but for programming test 1, I'll keep you posted. By the end of Friday, if I can make it earlier, I'll definitely make it earlier. And for your written test number 1, the guide example question, good. And review session tonight, 7:30. I will be driving home from outside, but I should be able to make it 7:30. But in case you guys don't see me in the Zoom, just bear with me. I should be there, but I'll make sure you guys got at least up to 1 hour to ask me questions, right? That's really your time. And for your lab number 3, it's going to be released after your written test number 1 on Thursday. So next week, during the scheduled lab session, you can start asking questions about lab number 3. Office hour, resume back to normal, and also TA information, just the same, right? You can always get the help that you need. Last week was a bit exceptional, but anyway, this week, resume back to normal. If you guys want to come to my office hour, I'll give you priority since you guys got test this week. Right, any question about the course? Alrighty, good. Let's do a recap, and we'll continue with the stuff about LTL, right? We're getting to the very heart of the language and the more interesting bit. So last Wednesday, we basically finished discussing about the syntax for LTL, right? So this will be more like a summary page for you guys. You really want to compare the parse tree, leftmost derivation and rightmost derivation. And we had quite a bit of discussion about why, for example, this subtree over here really corresponds to this part of the derivation steps for L and D, and also this part of the derivation steps for I and D, right? So you guys really want to make sure you understand exactly what it really meant. So in the test, you shouldn't really feel too surprised if I simply show you a tree and then maybe say, okay, consider this particular subtree. I want you to select the parts of the L and D or I and D about how they correspond, right? We explained very clearly last Wednesday about why we should only choose, for example, let's say here, we should only choose from step number 2 all the way to step number 6, but we didn't include step number 1, right? You really want to review the recording if you got any doubts. All right, that's something I would like to emphasize very quickly. And then we also talk about subformulas, right? It's just about really try to walk through the tree more thoroughly about each of the subtrees, which you guys learned about in 2011 or 2011 data structure course, right? Every subtree in the whole syntax tree itself can be derived into a formula. And of course, you want to be careful because formulas are not necessarily distinct. For example, you can see for this one here and this one here, they are the same, right? Which is normal. So if I just ask you how many subformulas do we have, you will say 10, including duplicates. But if I say how many distinct subformulas, you want to remove the duplicates, right? In this case, it will be make sure you don't really count P twice. Right? So these are the critical points you want to make sure you understand. One more thing, so whenever you got a parse tree over here, implicitly there will be some parentheses around each internal nodes over here, just to force the order of evaluation, right? Just the nature of the parse tree. We wouldn't get a chance to talk more about parsing theory, but in practice, sometimes people, when they define a grammar, they might embed the operator precedence, like a parenthesis as part of the grammar, but we don't do that. It will just complicate the matter for the discussion, so we don't need to. Okay. All right, so the 2 pages from last time over here are just about the final discussion of the syntax for the LTL. There's actually one more insight I would like to talk about just about the syntax, but I'll leave that maybe after your written test, because once you study a little bit more about the syntax for the written test, when I talk about the insight, you can appreciate that a little bit more. Okay, I can leave that for maybe next Monday. Okay. And last Wednesday, we started talking about the semantics, like a meaning for the LTL. And to really set the ground, we'll build a scaffolding. We have to understand label transition system. That's really the formal model we're using. Usually we'll present it either as a 3 like a tuple, or we present it like a diagram. Either way, right? You should get yourself familiar with either. So we talk about the set of states. Also, we talk about the transition relation, not a function, and also labeling function, right? We talk about all the three components. And also there's something called the labeling function over here, right? That one is really about which properties are satisfied in each particular states, right? So that's why it's a total function, right? So if you see the definition for P, it's actually a total function, okay? And we gave you this example here just to illustrate each of the three components here. And then we even try to maybe formulate deadlock freedom, for example, right? Just to see, to make sure we can make progress for each state. And since there will be some background study for you guys to brush up, you know, the sets and relations from 3342, I already gave you the slides. You should really study for that. Of course, you can ask me questions tonight if you want to have any doubts, or office hour later before your written test. And we spoke about for this condition here, so there are basically at least 1, 2, 3, 4 different ways to formulate the deadlock freedom property, right? You can go over them. And this one here about using range restriction, you can also think about it, okay? Okay, guys, any question about the LTS in general? Of course, we're going to use it when we actually define the path, and also see how we can define if formula is actually satisfied at different levels, as we'll see today. All right, so that's just another LTS. It's a pretty simple one, right? So you can also see the solution on the slides. That one there, you can also feel free to print out the page and try to do the problem yourself. That could be like a nice format for the exam, for example. I might just give you something slightly more complicated, but the format will be similar. All right, and then we start talking about path, really. So whenever you talk about path, there will be some implicit labeling function over here to say, for example, we got P, Q, and R. So these are the three propositional atoms which can evaluate to either true or false. And in the diagram, here we simply say this particular states satisfy P and Q. What about the missing R? Implicitly, R will be not satisfied. Okay, we're going to see example again today. You need that. You need to know that implicit assumption to evaluate the truthfulness of the formula, as we'll talk about today. Okay, we'll get there. All right, so we talk about labeling function here, right? We did that together, and also about the set of states, transition relation, etc., right? So I think this one might be more relevant about a running example we're going to use for all the LTL formula as we get more and more complicated about the formula format. All right, and I believe, yeah, so that's the last page we spoke about last time. Let's review that because we need this insight here. Whenever we talk about a path, right? Path is simply a sequence of infinite number of states because we talk about reactive system. So the system may never deadlock, or the system may never terminate. So we got S0, S2, S2, S2. It basically corresponds to this particular path over here, just one possible path, okay? And then when you talk about a path here, so we say that the very first state here is called S1. So when we talk about definition for different like a path satisfaction, or maybe about suffix, whenever you see S1, S2, S3, right? Don't get confused. So these are simply the components in terms of indices, right, of the path. We're just referring to different position in the path. So S1 for pi happen to be S0. S0 is simply the name of the path, right? That's something you want to get very clear, okay? And what about the path suffix? That's basically the last concept we spoke about. And we did some little exercise here. I'll mention that once more because we're going to need that later. So path suffix, you cannot say path to the power of 0 is simply undefined, okay? And pi to the power of 1 simply means, given this particular path called pi, I want to extract another path. That path is going to start from the first component of pi. In that way, the first component is right here, so this is going to be the path I'm going to return. That one is pi to the power of 1. And pi to the power of 2, in a similar way, I said I want to extract another path over here, and that path is going to start from the second component of the path, right? Okay, so that's the pi to the power of 2. And we did this little exercise over here, and this one here, you might also, we might need it again when we talk about some other LTL formula, okay? Let's look at this once more, okay? When I say pi to the power of 2, and then to the power of 3, of course, you shouldn't really just say pi to the power of 2 plus 3. It doesn't work that way, Okay, I know that works in math pretty well, not in this context. Okay, I would say the best way for you to really solve this problem here is just visualize it. That might be the best way. Okay, so you will start with pi to the power of 2, meaning that I'm going to extract a path starting from the second components of the original pi, first of all. And then this path that's returned is the new path I'm considering. And then I want to take that to the power of 3. That means 1, 2, and 3. Starting from its third components, I want to extract another path. So this is the final answer, right? Which is equivalent to the path starting from the fourth components of the original pi. So that's why I wrote it here, pi to the power of 4. Okay? So this little exercise here really gives you more insights about how the suffix notation can be manipulated, right? So of course, if I give you even more to the power of, for example, 4, you will know how to compute it, right? You just go with it in a similar fashion. Okay? Any question so far about the recap? We good? Okay, very good. So let's now do one more little exercise just to see this diagram a little bit more insight here, and then we'll talk about definition for evaluating the formula, right? That's really why we have been doing so many things about syntax, LTS, for really. Okay. Okay, let me just go over the slides you should really look at is this slide here, slide number 32. And guys, by the way, for your written test number 1 on Thursday, you will cover up to and including 31, right? So whatever we talk about today, in some way, you don't need to worry about it for Thursday. Of course, you got to worry about it later, right? So still ask me questions, okay? Okay, let's start from this, okay? Slide 32. Odd possible path, okay? Basically, you want to somehow, given a diagram, you want to somehow do a process called unwinding to really see how many possible paths you may have so that when you evaluate the formula, you will be able to analyze from different cases, for the path, right? So unwinding, okay, I'll just show you the final outcome first, and I'll show you how you derive that, okay? It's not very difficult. Let's say this is our LTS, or the diagram, which you can formulate as LTS. This one here basically suggests cycles in many cases, right? For example, you got S0, S1, S0, S1, that's one cycle. Or once you get to S2, 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 that's another cycle, right? There are other instances of cycles as well. So if I somehow want to get a little bit better idea about how this system is going to behave, I can unwind it and I'll get something like this. It's kind of easier for me to see like a tree structure. So I can imagine how I can traverse the tree, right? So let's see how I can come up with this tree. That's something I want to show to you from scratch, okay? So let's say you're given this graph over here, okay? That's the running example, okay? And the process we're going to perform is called unfolding or unwinding. Unfolding or unwinding. We're just going to see the different patterns that will go infinitely, go with an infinite number of states. Okay, that's the process we're going to go. Right, just to make it a little bit easier for us to see. Let's, of course, S0 is a starting state, right? Usually we just see a single arrow over here pointing to the states. That's a start states. So this will be the start states. And then let's say from S0, we got 2 possible paths going out. You can see that it's either here, either we can go here, or we can go here. Only 2 outgoing arrows over here, right? So that's the 2. And then once we go to S1, we may go back to S0, okay? For that one there, let me just use orange, okay? And then when I unwind, I'm just trying to follow the color convention to see how the unwind will go. And then from S1, there's only one, either we go back to S0 or we can go to S2, right? Let me use that for purple for that. Okay, one more. So once we get to S2, there's only one choice. You can only do a self loop for as many, for infinitely number of times. All right, so that's the different, So that's the different parts we want to recognize. Basically, I cover all the transitions, right? We're going to see how to unwind these transitions. So whenever we say unwind or unfold, we are really talking about transitions. All right, Let's now start with S0. Okay, that will be the starting state right here. Okay, and we know that it can branch out to either S1 or S2. Okay, let's do the S2 first. S2 is very straightforward because once you get to S2, you basically have no way out. Just go infinitely, right? So after that, you're simply just going to go for S2, and then S2, and then dot dot dot. All right, that the right subtree is actually quite straightforward, right? What about S1 here? From S1, you basically can either go to S0, or you can go to S2, either way, right? Let's talk about S2 first. So once you go to S2, which is the purple one, you can see here S2 is really corresponding to something that we have already identified earlier. So whenever you basically go back to the states that we have visited or analyzed before, you can basically just copy the same recurring pattern for the states, for the transition, right? So you can think about this will be the one occasion where we got a recurring pattern. Pattern for S2. So you can think about for that one there, we don't really need to do anything. We don't need to analyze again. We can simply just copy this one here and then paste it right here, and so on, right? Whenever you see any state you have seen before, you can just apply the recurring pattern, right? That's one occasion, okay? Over here and over here. Okay, let's see one more. You can see we have already analyzed S1 going to S2, but it may also go to S0. This one is slightly more complicated, but just another instance of recurring pattern. So that one there, I'll take orange, and then I will get to S0. So when I get to S0 over here, right, that's a second occasion. So you can think about star here corresponds to this guy over here. What does that mean? That means whatever that's going to happen right here is going to be a tree, can be infinitely large. It's just going to repeat a pattern that we have seen so far for S0, which is basically like this. All right? So this pattern here, how can I do it? Okay, I'll just do the following. You can think about I'm just going to copy this part over here. This is the pattern we have already identified for S0 so far. I'm just going to copy that, and then let me just erase this one for now, okay? And then I can simply paste it. Right? It's going to continue infinitely, right? So this one here, I can just change the color, so that will be just S0. The reason that I really want to build this from scratch for you is you don't once you get to S0, you don't really have to really do the unwinding from scratch. You can simply know that I already have analyzed S0 before. I can just copy and paste the pattern conceptually, right? That's something you want to keep in mind, okay? Yeah, see here I got a little bit cut off, but you can see S2, right? Goes all the way. All right, so this diagram here is not that complicated, but I'm just saying if I give you something slightly more complicated, you will know how to do it, right? And of course, this one here is going to be another repeating pattern for S0, right? And of course, you can just copy and paste again. Okay. All right, any question about this? Unwinding, unfolding exercise. Yeah, Adrian.
So we can say that every subtree of this tree that is rooted at some state is the same.
Yes, you can say that. Yeah, for S0.
Ignoring order of elements.
Yeah, exactly. Yeah, you can say that. Yeah, of course, the tree itself is infinite large, right? It's not finite. So you can say this subtree here is going to be just the same as this subtree over here, which is just the same as this subtree over here, right? Okay. Very good. Okay, if you guys are okay with it, let's now move on about definition, right? So from this point onwards, we're going to use this diagram here we don't really have to go back to this tree necessarily, but it's just a technique for you to really absorb. That might be useful, maybe doing the test or doing the exam. So now we're going to talk about two different things. Okay? And let me just summarize right away on a new page, and then just like a preview, and then we're going to go talk about them. Okay. So let me just do that right here. Okay, good. We're going to talk about two so-called satisfaction relations. And we'll look at the definition in just a moment. But let me just talk about them right at first. Because whenever we want you to evaluate a formula, you want to know which one I'm really asking. I might be asking about one, but not the other. There are two different relations. The first one here is called a path satisfaction relation. I'll just say path satisfaction. Basically, given a single path, I want to know if the path is going to satisfy the LTL formula. So I have pi, which is a path. I want to know whether or not it will satisfy, right? We have seen this symbol before, but we're going to say it just satisfies, right? Whether the path will satisfy some LTL formula, right? So think about this one here. It really means satisfies. And this one here is a path. And this one here is an LTL formula, which you guys know pretty well about how to derive a valid one, right, from the grammar. That's why we had to do that exercise before we talk about this, okay? So that's going to be a valid LTL formula. Okay, we're going to talk about path satisfaction first to see its formal definition, which is pretty straightforward, but I'll get there. The second relation we're going to see is called model satisfaction, okay, at the model level, which will need to consider different paths, basically. Okay, it's called model satisfaction. Okay, and to be very complete and precise, you'll be given, so here you're only given a path, right, just a single input. But for the model satisfaction, you'll be given two things. One will be you're given a model, of course. Okay, so you can think about this model here is the LTS that we spoke about last Wednesday. So this one here is a model formulated as an label transition system, right? Which is a triple, right? Also with the P, the labeling function. Okay. There's a model, and then we got another input. And we just say a little s over here. Okay. And if you remember, we actually said M here is simply a triple, which will be S, capital S, and also transition relation, and also we got that, forgot the symbol. Beg your pardon. Yeah, L here, labeling function. Beg your pardon. There we go. All right. And you can think about the little s over here is assumed to be a member of the capital S. That's the connection I want to draw very quickly, right? Think about the S over here is really a member of the capital S here. Okay, so these are the two inputs. And we want to know whether this model here will satisfy some LTL formula that's valid. So satisfies some LTL formula. So we got path satisfaction and we got model satisfaction. And typically, the model will be quite clear in the context. So you just don't need to mention the model. Maybe it's something mentioned in the very beginning of the question. So for different parts, I will just mention about the states that's being checked. Okay. Okay. One more thing to say, but we're going to see the formal definition later. You can think about the number 2 is more like a generalized version of number 1. For number 1, you only consider a single path that's given. But for number 2, you're basically considering all the paths starting from state S. You want to make sure every path there is like a universal quantification will satisfy this particular formula. Okay? I'll write it down informally, but we're going to formulate it. So what you say is, we need to consider all path starting from states S. Okay. Yeah, we should be able to actually cover some example. Well, definitely path satisfaction, but also get to put side by side. How about the path and also the model, right? So these are the two. Okay. Okay, and then let's see some slides and see some definition, right? We'll start with something very simple, and then we'll try to build up with more complicated formula. Okay. So what I will do is, okay, let's start with K. Here we go. Okay, let's start with the path satisfaction, right? Which we already mentioned. That's number one. Okay. So you got some model here. Of course, the path should be relative to a model because path consists of states, and states should be defined by the capital S over here. So if you got some path, let's say start state is S1. Could be S1, can be S0, depending on the example. But when we talk about definition, we always say S1 as the first state in the path. And we say that if the path will satisfy the formula, what does it really mean? That we have to define this in the following way, right? I'm going to talk about them one by one with you, okay? So here we are only talking about using the operator of propositional logic, right? You can see we got conjunction, we got disjunction, we got implication, right? And also here are the definition for what it really means. But I'm going to go over with you one by one, okay? Let's see here, all right? And then there's a little exercise that we can do at the end as well. I'll reveal that maybe in a moment, okay? We can talk about it. So if a path satisfies some proposition, right? We can use conjunction, disjunction, implication, negation, true and false, and maybe some propositional atom, right? So these are the different ingredients or components in the grammar, okay? What does it really mean when a path pi satisfies a particular propositional atom over here? What does it really mean, right? We're going to go over one by one. The definition is simple. A path will satisfy a proposition if its initial or very first state will satisfy that. That means when you are given a path that goes infinitely long, if you're asked whether the path will satisfy some propositional formula, all you got to do is you only look at the very first state, and that's it. You can disregard the rest. You don't need to worry about it. As far as the evaluation with satisfaction is concerned, you only look at S1. Okay? So that means S1 is the only state you're concerned about if you're evaluating propositional formula. Okay? That's the definition. Okay, so this is the first states of pi. Okay? And we only have to see whether or not this S1 will satisfy each one of them. Okay? Let's see the definition first, and then we'll see some example. Okay? First of all, we want to know whether or not the path will satisfy P. P is maybe some propositional atom, right? I'll draw some very quick connection. If you recall, when we talk about LTS, we talk about P can either be some propositional atom here, or can be something here, right? That's what we spoke about. Or can just be PQR, like in this diagram, or can just be PQ or R. Okay. Okay. Let's now go over definition. And this one here is defined as, so this will satisfy if and only if, okay, that the P that we try to evaluate is a member of, if you remember the labeling function, right? The labeling function can tell us what are all the propositional atoms that will be satisfied on the particular states. And now I'm only interested in S1. Okay, this is a very important base case over here for us to know. So if you look at this one here, this one tells you the set of all propositional atoms satisfied in the first states S1 of pi, right? That's really what that's really what it means over here. Okay, good. And then we talk about true and false. We're basically just asking whether the first state will satisfy true and if the first state will satisfy false, right? That's really what it means. This one here is really asking whether the first states of pi satisfies true. And true is always satisfied. So this one is always true. Similarly, false is always dissatisfied. So it will just be false, basically. Okay. And then let's look at this one here, right? This one is more like a recursive case. So think about all these are the base cases. All these are the base cases. And the rest is you're basically given some formula phi, which can be derived using the grammar. We want to know whether or not if you put a negation in front of phi, would that be satisfied? If you try to have phi 1 and phi 2, each one of them individually is a valid LTL formula. If you put them into conjunction, is the formula going to be satisfied by the pi? Right? And etc. Okay? So these are the recursive cases. Okay? Let's look at the definition very quickly. Okay? This one here is interesting. If I actually got some phi over here, I simply want to put some negation. What I can do instead is, why don't I simply try to see whether or not pi can satisfy phi? Whatever result I got, I can just put some negation outside. Okay, that's something we'll see a little bit later. So for the first one here, it will be if and only if I can try to see whether or not pi will satisfy the phi. Whatever result I will get, because I want to know whether or not it should really satisfy not phi, I should negate the result at the end. Okay. This one tells you, basically, if I want to ask you to really evaluate this, what it can do instead is to take the negation of this one here and try to find the result, and then just negate the result. Okay. Similarly, if I got phi 1 and phi 2, individually, they are simply just propositions. Rather than evaluating their conjunction, I can evaluate them individually and then combine the result using conjunction. Okay. This one, if and only if, I can try to evaluate phi 1 over here. I can also try to evaluate phi 2. Each one of them is going to give me either true or false, right? And then I can simply say, I want both of them to be satisfied. So why would this be useful? This would be useful if phi 1 and phi 2 individually are complicated. In which case, if you try to combine these two complicated formula and evaluate them together on a single state, it may not be as efficient or as effective. What I can do instead is to break them down into two parts that can be evaluated independently. Okay, that's what you can do. But you can do either way. Okay. Okay, very similar. So let me just write down the complete definition as well. So here will be if and only if I can do phi 1, and also here I can say phi 2. I can put disjunction, right, in a very similar way. And finally, I can do pi phi 1 and pi phi 2. And since I got implication here, the result I got from each, one of them can be the antecedent. The other one can be the consequence. Okay. So just pay attention to this. So you can see not here, conjunction, conjunction, disjunction, disjunction, implication, implication. All right. We'll see example very soon, but I just want to go over definition with you first. Let's now, based on this definition here, let's now do some very simple exercise over here. Okay. Okay, over here. Now we want to express some predicates. Okay. And we're going to somehow apply the path satisfaction. Right? So the definition is right here. Okay, right here. We want to write a predicate that will express all the even number states will satisfy some propositional item P. Even number states. Okay? For that one, I can let you know what they are very quickly. For even number states, it will be S2, right? S1 will be odd number. That's the first states. So we got S2, we got S4, we got S6, and etc. Right? How will we satisfy? How do we specify that? Of course, in order to do this one here, first of all, you want to know how to somehow range over all the even numbers. That one I'm pretty sure you can do, right? And then once you get an even number, you can use the even number as the index of the path suffix, right? Somehow. And from there, you can apply the path satisfaction definition here. Since we are talking about the P here, is a particular propositional atom, so it should really be applicable to this particular rule over here, right? So that's what you got to do. Think about it just for maybe 1 minute, and then I'll go over the answer with you. Might be a little bit jump right now, but I think it's a nice exercise to see. Okay. Okay, I will put a star here, and I'll put the answer here. Good. Now take 1 moment to think about how you might specify that. Anyone want to contribute any answer before I go over the answer? Daniel, please. Absolutely. So the universal definitely has to go over all the even number. How would you go about that? Why don't we say for every I, let's use I. Somehow I can be used to say the index, right? 2, 4, and 6. How do I say that? Go ahead. Yeah, exactly. So something like if you can say I modulo 2 is equal to 0. I'm pretty sure that's what you meant. And then we're going to say this, right? So here, what would be the range for this universal quantification? It's going to be exactly 2. Well, you may also want to say it doesn't include 0, right? I larger than 0, okay? In that way, this part here is going to tell you I is going to be 2, 4, 6, exactly the S2, S4, S6 that we are talking about, okay? Let's now, first of all, just make sure it's in place. So it's going to be 2, 4, 6, etc. Right? But somehow we want to say state number 2 is satisfy P. State number 4 satisfy P. But so far we haven't really talked about a states satisfying some formula right away. We talk about only path. How do I go about that? Okay. For that one, I'll give you guys the answer directly, but you got to think about it. Okay. So I can say basically something like this. Pi to the power of I, all right, satisfies P. All right, for this one here, let's try to understand what's going on here. If you only look at this part here, that one needs the knowledge about path suffix. So this is the path starting from the ith components of pi. Right? If you think about, for example, second components, fourth component, and sixth component, etc. Right? So this part is really the critical part. And then if you think about what's going to happen here, And this part here, by definition, right? We also talk about if you're given a particular pi, what does it really mean for the pi to satisfy some propositional atom? It simply means that particular states, right? The first states. The very first states for pi to the power of I would just be Si. Right? And when you say that one will satisfy the P, by definition, P should be a member of the labeling function, right? Over there, right? Still a little bit abstract, but we're going to see example in the next page. Okay, you can think about this. This is Si, and then we're going to apply the labeling function over here. And then, since we're asking about P, so P is a member of that. So this is another way to express that. Well, it's like a definition for the path satisfaction. So this exercise here really puts many things together, right? About universal quantification and also about path suffix and also path satisfaction, right? Many things together. Okay, just for your information, this is another alternative version given by your fellow student back in winter 23. I'll just put it here, right? There's another way to formulate it, which is equivalent. So here you can simply say for every I, rather than using modulo, let me use natural number. Let's say I is a natural number, and also I better be positive. Of course, I can say 1 here if I want to, but let's just make it more explicit. So here I can be 1, 2, 3, 4, 5, right? How do I go from 1, 2, 3, 4, 5 to 2, 4, 6, etc.? I can say pi to the power of 2i. That will work too. All right? Because over here, I is going to be 1, 2, 3, 4, 5 multiplied by 2, 2, 4, 6, 8, 10, etc. Right? So it will work. You can go for either way if you're asked to do something like this, right? Of course, there are different ways to really express the same logic, really. All right, any question so far? We haven't seen any example yet, but I think it's good to go over definition first, get some intuition and see how complicated things might be, but once we see the example, it's not too bad. We're going to apply them. Okay. All right. Let me just go over a few more definitions, and then we'll do example throughout. Okay. So that's about the path satisfaction for propositional logic, right? You can see logical operations, and we're going to see path satisfaction for temporal operations. So now we're going to see some temporal operators. Okay. So what I would do is I'm going to show you the slide. It's going to be slide number 34. All right. So given the same model and also some path, we're still talking about path satisfaction. We're going to define the next operator. We're going to define the global operator. And also we're going to define the future operator. So these are the three things, the three operators we'll talk about first. For until, release, weak until, we'll talk about them a little bit later. Okay? So let's focus on these three, the most foundational ones. Okay? I'm going to go over the definition with you and try to give you some intuition. Okay? So we're still talking about path satisfaction. Okay? So we say that a path will satisfy this particular formula. You can see we got the next operator. Okay? You can see the x over here is the next operator. And the next operator is applied to some phi, which is assumed to be some valid LTL. Can be arbitrarily complicated. So the phi over here is some arbitrarily complicated and valid LTL. Valid, arbitrarily complicated LTL formula. All right. And let's look at the formulation first, and then we'll visualize it. The formulation goes like this. If I got some pi, right? We'll talk about path satisfaction. And whether or not the path will satisfy some next operator formula, right? If and only if. The definition is pretty simple. Since we talk about next states, the current state is S1. What about next states? S2. So you will just say pi 2 satisfies phi. All right, the definition as simple as that. So this pi 2 over here is basically a path starting from the second components of phi. Okay, let's look at that visually. Let's say this is pi. And we got S1, S2, all the way to, infinity. And when I say pi satisfy x phi, when I say pi satisfies x phi, it would be as if I go to path suffix starting from the second components. So you can think about this one here is pi to the power of 2, this part here, right? I'm basically asking whether or not pi 2 will satisfy phi. That's what I'm asking. Of course, it really depends on what phi really is. It depends, but we'll get there. Okay? If phi here is simply some propositional atom, like what we said earlier, then you only need to look at the very first states for this pi 2. Right? That's something we'll see. Okay. So this will be just asking whether pi 2 will satisfy phi. Now, I want you to do some very careful comparison here, right? If you look at this one here, let me use a different color. If you look at the orange one here, and you can also look at the pink one over here. So these two satisfaction are equivalent, but the difference is the orange one has to worry about the next operator. The pink one here already got rid of the next operator. That's the difference, right? We just move our context to one state to the right. So we're considering this path specifically. Okay? Any questions so far about the formulation? All right, let's play a little bit more about this definition here. Okay? Now, I'm going to put it here. Question. Given the definition here, and given that we got pi 3, given the definition here, and also you can see somehow we got pi 2, but now let's say the pi here is actually pi 3, pi to the power of 3, right? So the presentation is not exactly good, but this one here is really pi to the power of 3. Okay? We are basically asking what exactly is being evaluated when we say pi to the power of 3 satisfy next p. What are we checking specifically? And this will have to do with the suffix exercise we did last time. That's why I wanted to do that with you last time.
It's checking if P is an L of S4, or in other words, if P satisfies S4?
That's exactly right. Because somehow we did the exercise last time, and that double, like a nested exponent, will just boil down into pi 4. Okay, but just for your fellow student, I'm going to do it from scratch again. All right, guys, so let's see how we can derive this one here, okay? So let's go with definition, right? You always want to go with definition. You have no clue, okay? So what we got to start with is, if we are checking, let's say, pi to the power of 3, right? That's what we're given. Whether or not it will satisfy this formula here, which will be next p. And of course, p here is some propositional atom. Okay, let's go with that. By definition, so the pi here can be arbitrary pi, right? So pi here, we're just replacing it by pi 3. That means the pi here is basically pi 3. So it would be as if pi to the power 3 and then to the power 2. That's what we're doing. Okay? So this one here, if and only if, first of all, we start with pi to the power of 3. And then that one there should be to the power of 2. Will satisfy. Now we can get rid of the next operator, which just be p. Are you good with it? Right? I just replace the pi here that's in the formula just by pi to the power 3, and then you do the rest for the replacement. Okay? And this one here, you guys know pretty well, right? You can refer to the exercise from last time. Again, I will refer you to it. That one there will just boil down into pi to the power 4. Okay? You can see exactly how it can be done. Let me not repeat it. So this one here will be if and only if pi to the power 4 satisfies p. And then I know that it will just be, again, since this is a propositional atom, right? I only need to worry about the very first states for pi to the power 4, which will start at the fourth components of the pi. P is a member of, basically, labeling function S4. All right, you can see this exercise here, again, applies many definitions we learned earlier. So it's really worth your attention. All right. Let me draw one more diagram to help you, right, when you review the exercise. Okay, let's do it once more. Okay, we're talking about this exercise here. So let me start with the pi again. Let's say pi will be, in general, S1, followed by S2, followed by S3, followed by S4, followed by S5, etc. Okay? So here we are basically asking whether or not, so we got pi to the power 3 and to the power of 2. That one we know pretty well. This part over here is pi to the power of 3. All right? And then we're going to choose the second one here, right? 1 and 2. So this is pi to the power of 3 to the power of 2. Right? That's what we have. And basically pi 4. And we're basically asking whether or not this particular states will satisfy p. Okay? That's what we're doing. Okay? It really boils down into S4 right here. All right, any question about this exercise? John?
How come we don't define like pi to the I is pi to the I plus 1 satisfies it? So like pi satisfies x pi is the same thing as pi I plus 1 satisfies.
You mean pi to the I plus 1?
No, so like pi satisfies x pi is the same thing as like pi to the I plus 1.
Where's I? We don't have I here.
In the first one. So pi to the I.
Sorry, are you talking about this definition here?
Yes. So if we had I as the
we don't have I here. Where's I?
okay. We assume it's
If you talk about I, you're maybe talking about we are within the context of some universal quantification, for example, but we don't have it, right? So here, I can send it, you talk about I and I plus 1. But that one is, even that is not general enough. We're saying that if you're evaluating this formula with respect to some pi can be anything. Pi can actually be maybe pi to the power 3. Pi can actually be maybe this complicated past suffix, doesn't really matter. Whatever pi that might be, you will only look at the second components of that particular pi in order to evaluate the next formula, right? So when you say I plus 1, I don't see I here, right?
like the state it's starting at, that path, the initial state of that path.
The initial state is just pi 1, right? So here, if you say the second state, it will be pi 2. There's no other way to say that. Yeah. Okay. Good. All right. Any other questions about this? Right. Again, definition. Right. All right. Let me go over 2 more definitions, and we'll take a short break. And after break, all examples. Okay. I want to just get rid of all the definition first, so we can just do example to make sure you totally grasp the idea. Okay. 2 more. So that's the next operator, and The next two temporal operator is about global and also future operators, right? Another two, okay, quickly. And these two nicely correspond to the universal and existential quantification. If you guys remember when I first presented the grammar for LTL, I said we don't really have the for all exist over there because they're somehow embedded in the temporal operators. Okay? In these two operators, you will see. As part of their definition, you will have to use logical quantification. Okay? Let's go one by one. And we'll still talk about past satisfaction. So G here is so-called a global operator. Okay, global operator. But there's also people like to say the following. If I say globally, phi is true, that'll be the textbook way of saying it. Okay. Another very practical way of saying that among the practitioner, you can also say, henceforth, phi is true. Intuitively, phi is always true, basically. That's what you're saying for every state. And let me talk about the other one very quickly, just to give you the alternative meaning as well. So for the future operator, of course, you're going to have F here really means the future. Sometime in the future, I don't care how distant or how close the future is, sometime in the future. Okay? And this one will make sense. In English, if you say sometime in the future, that means eventually, as long as it happens. Okay? So here, if I say in the future, phi will be true, that means eventually phi will be true. Phi is, you can say either phi is established or it is simply true. Or just say it's true. That might be more intuitive. Right? Just by seeing the meaning, you can already kind of imagine which one should be universal, which one should be existential. Right? But we're going to talk about it. Okay? Let's now go over definition very quickly. Okay? So we still talk about past satisfaction. The way to write it is something like this. I got some path pi, right? And the path satisfies globally true phi. Okay? By definition, this will be satisfied, it will evaluate to true if every state in the path satisfy it. Every state, well, that means the path starting from the first component will satisfy it, the path starting from the second component will satisfy it, and etc. So we're going to use that past suffix notation to really help us define this operator. Okay? So the formal definition you will see on the slides will go like this. If and only if, okay, we say for every, and we're going to use our I here as the index for the path components. For every I, and then we say I larger than or equal to 1. And then we're going to use the I as the exponents for the past suffix, right? Pi to the power of I. So John, you were talking about I before, so you can only refer to I if you got I here as a dummy variable, right? Yeah. Maybe that's what you meant to say in a different context. So here we say satisfies the phi. So one thing I want you to notice here. If you look at, for example, here, versus here, right? Because these are the two places where we're using the satisfaction relation. For the orange one, we are trying to check the past satisfaction where the formula contains the global operator. We can somehow get rid of the global operator by evaluating the phi on every possible states on that particular path. That's what we're doing. Okay? That's the definition. And on the diagram, in some ways, very simple. If I got a path like this, what should I do in order to show that this formula is satisfied? I basically have to do the following. I got to check for S1, I got to check for S2, and check all the way through. Of course, you might argue that if it isn't that infinite, will my check ever terminate? Well, usually the path over here might contain a cycle, so you can argue about the pattern. That's why we kind of do the unwinding, unfolding exercise. So once you see the pattern for that, excuse me, once you see the pattern for that particular infinite path, you just have to figure out what are the states over there. So for every state that appears in this infinite path, as long as they all satisfy phi, you'll be fine. Okay. So you basically want to make sure the first state satisfies phi, the second state, and all the way to the end. That's what you got to make sure. Any question? Vincent? Aha, it's a good question here, Vincent. I wanted to mention that. Okay, it's on my notes actually. Okay, Vincent was asking the following question here, which I'm going to ask you guys, right? By the way, this may be related to your written test number 1 on Thursday. All right. Can I simply replace I is a natural number? Can I do that? Anybody? Ferrets, why not?
You need to say I is a natural number starting at 1, so n1.
Okay, n1, we can say I larger than 0. But the question is, why just writing I is a natural number is not good?
Because then you could, it could be 0.
Can be 0.
Yeah.
And we said pi to the power of 0 is not undefined, right? Good. Okay, that's exactly, Vincent, that's exactly why. Okay, so this one here is not good because when I is equal to 0, pi to the power of 0 is undefined. All right. Of course, you also cannot say I is a member of the z, like a set of integers. Also, I to the power of -1 also is undefined. Right? Past suffix is only defined in positive numbers. Yeah. Good. Okay, guys, one more, and then we'll take a short break. Okay, one more. So that's about the global or henceforth operator. One more. And that one is about the future or eventually operator. Okay, that one there is just kind of symmetric. Before we say that every state in the past should really satisfy it, but now we go a little bit more the other extreme. At least one state satisfying will be enough. All right. So let's now see the definition here, and then we'll do some little bit visual illustration, and then we'll take a short break. So the way you do that would be pi here, any arbitrary path satisfies, and then I'm going to say the future operator. Oh, sorry, I just may make one more note. Okay, if you remember, we said earlier, the global operator, you can also use the square, right? Also in the literature, you can also say square and then phi. That's also fine. Okay. And the future operator is a diamond, right? If you go back to that table I summarized earlier, maybe last Monday or maybe before the reading week, I forgot. Maybe last Monday. You can take a look. Okay. All right. For this one here, if and only if, okay, there's at least one path. Sorry, at least one state components in the path that will satisfy that. It's either maybe the path starting from the first state components, or maybe the path starting from the second state component, or either way, right? As long as phi is satisfied at some point in the future, and given that the path is infinite, as long as it gets satisfied at one point, that'll be fine. Doesn't matter how long it will take. Doesn't matter. Okay. So all we gotta say will be there exists I. Okay, I larger than or equal to 1, and pi to the power of I satisfies phi. And one more highlights. If you look at, okay, if you look at this pink formula over here, and also this orange formula here, right? So these are the only two places where we are using the satisfaction relation, right? So you can see here in the orange, we do have the future operator. By getting rid of it, we just need to check at least one state that will satisfy that particular phi, right? What about visualizing it right here? That means if I look at this infinitely long path, as long as one path, as long as one state will satisfy it, I should be okay. For example, let's say this particular one, right? So you can think about as long maybe this one satisfies phi, that'll be enough. Okay, not really every state. So this is a much weaker property, and whereas this one here is a much stronger property. Right? Any question? All right, if you're good, let's now take a short break for 3 minutes, and we'll take attendance, and then after the break, we'll do examples. And we'll continue for sure on Wednesday as well for examples. All right, we got about 10 minutes. I think I just want to go, we have gone over quite many definitions today. I think you guys will need some time to digest before Wednesday. Of course, you got to get prepared for your written test number 1. But on Wednesday's lecture, we're going to do lots of examples, maybe for most of the lecture time. We should really do that to make sure you're comfortable with the different notion about past satisfaction versus model satisfaction. I haven't really given you the definition of model satisfaction just yet. We'll do that in the beginning of Wednesday. I just want to do 1 page of example today. Okay, just 1 page. Simple one, but we can do it. All right. Let's do just 1 case over here, right? If you recall, before the break, we spoke about when we talk about past satisfaction for some proposition. One of the base cases would be if I simply give you some propositional atom right here, and then it will just boil down into whether or not that propositional atom is a member of the labeling function applied to the very first states of the path, right? That's what we said earlier in the before the break. Let's just use that particular definition to see how we can do different check. Okay, let's do this one here. And let's say we're given this diagram here, and the pi that we are talking about should be a valid one. So S0, S1, S2, S2. So I'm talking about basically, I start with S0 right here, and then I go for S1, and then I'm going to go to S2. Once I go there, I get stuck, basically, right? So that's the path I'm talking about. It's a one valid path, pi. That's the pi I'm talking about, okay? And I want to see for the same pi, right? The same pi. So on the left-hand side, I just got the same pi here, okay? As a little bit preview for Wednesday. For Wednesday, we're going to see on the left-hand side, what if we change from pi into just one state? Then we'll move on to something called model satisfaction, right? That's for Wednesday. But for now, it's basically just a path, right? Okay, so let's now talk about each one of them. Okay, this base case here, I'm asking whether, just before that, so by definition, if I'm asking whether or not the pi is going to satisfy some propositional atom P, we're basically asking whether P will be a member of, the first states in the path. What's the first states? S0, okay? So S0, you can think about this is the S1 of pi, okay? So we only worry about S1, which is this guy here. We are only worried about this one here, okay? So this one is the S1 of pi. And we know that one there is satisfy P, satisfy Q, and implicitly not R, right? R is not satisfied. Let's talk about different cases here, okay? So when we say the path satisfy true, does S0 satisfy true? Always, okay? So that one there will just be true, okay? Yeah, this one here, just a notation here, okay? We are basically asking, does S0, the first state of pi, not satisfy false? It does not satisfy false because false can never be satisfied. So this one here will be true. Another way of asking this is like this. If I simply say pi false is equivalent to, okay, you can think about this / like a negation. It would be as if we say not the case, pi satisfy false. No states can satisfy false. So this part over here is simply just false. So by applying negation to false, we just get true, right? That's how I got it, right? Just rewrite it a little bit to show to you. All right, it's going to be a little bit more interesting right here, right? And as I said earlier, since we are now only worried about S1, right? S1. So S1, which is S0 right here, right? P and Q, are they both satisfied? Yes, because P is here, Q is here. They're both listed. They're both members here, all right? Yes. Another way for you to think about this is like this. So let's say, if you think about this one here, evaluating this would be equivalent to pi satisfies P and pi satisfies Q. And then I know that this one here, by definition, is basically asking whether or not P is a member of the very first state components of pi, which is S0. The capital P, the labeling function, right? That function there. L here, and then I got S0. Indeed, P is there. And also this one here, what about Q? Is Q a member of the labeling function applied to S0? Yes, indeed. Right, so that's why it would be true. You can definitely try that. Okay. Okay, this one here, I know at least P will be there. So it's a disjunction. If conjunction is already satisfied, disjunction must be satisfied, right? So this one here will also be true as well. And for this one here, you can feel free to say, to evaluate this, it would be as if I can try this or try this, right? All right, let's see one more. How about this one here? P implies Q. Should be, right? This will be as if pi satisfy P implies pi satisfy Q. And we know that both P and Q are satisfied, so we're going to get true implies true. And then it's going to give us true. All right. Next one. How about this one here? False, right? Because R is not listed there. So it's not satisfied. So this will be boiling down into whether R is a member of the labeling function applied to S0. Labeling function applied to S0 will only give you P and Q. So R is not a member, right? So that should be false. Final one. How about here? True or false? True. Okay, this one's interesting. Well, again, you can, if you think this formula is a bit too complicated, let's say you don't decompose it. R here, we know that it's already not satisfied. So we already got false antecedents, right? False implies anything. That's a zero of implication as a review, okay? Or you can try also to say that's equivalent to pi satisfy R implies pi satisfy P and Q and R, similar. And I know that this one here is false. And false implies anything. So overall, it will still be true. All right. Something you can try. What if I change all the left-hand side over here into pi 2? All right. So for example, here, I just got pi to the power 2, pi to the power 2, etc., right? And one of them will be, for example, true, and then you got false. And also, for example, you got the last one. Oh, beg your pardon. R implies P and Q and R. That is something you can try as an exercise. But in order to solve this exercise here, let me say that, and then we are done. Okay? If you look at that one there, you want to really look at pi to the power of 2, right? Pi to the power of 2 is basically the path starting from the second components of the pi. So what will be the first states? S1. All right. So here, that means you got to look at S1. This stay here. So every formula that we checked earlier, rather than evaluating them on S0, you're now going to evaluate them on S1. Okay? That's something you can try. Very easy to see. Any question? All right, I think about time. Thank you so much. And then tonight, 7:30, if I run a little bit late, please bear with me. No later than 7:35 or 7:40, but I should be there in time, just in case. Okay, I'll see you there, but meeting will be recorded, and then if you cannot make it, I'll make it available tomorrow. Okay.